Hello, everyone. Today my topic is consecutive reactions. In my previous 3 videos, we have studied in detail about parallel reactions and opposing reactions. The third one is consecutive reactions. It is not possible to elucidate the exact values. Therefore, kinetic law require careful planning or many experiments to study the influence of product and reactants. This has to be done due to the velocity data variations. In today's topic, we are dealing with consecutive reactions. Consecutive reactions are those kind of reactions in which the product obtained, A, goes to form B. So A is the reactant here, forming the product here. This product obtained is in first stage. Now product obtained in this first stage react further with each other or with itself, that is within itself or with the reactant. That is, this product will react with the reactant to form new products. So the consecutive reaction proceeds in stages. Let us consider an example, a simplest case of a consecutive reaction in which both stages are of first order. Suppose the initial concentration is A, or suppose A is the initial concentration of reactant A. So let X be the concentration of A, Y denote the concentration of B, and finally Z denote the concentration of C, respectively with in time t. Therefore, we can write this as X plus Y plus Z is nothing but A. Thus, we can say that the rate of disappearance of A is equal to dx by dt. Since it is disappearance, we will denote it with the symbol minus. That is equal to K1x, where K1 Is the rate constant? For A to B. Now this equation can be written as minus dx by x is equal to k1, move this here, dt. On integrating, we get minus ln of x is equal to k1t plus I. Where I is the integration constant. But at t is equal to 0, that is at 0 concentration, when no reaction has started to take place, that is at 0 time, we will have x as A. X will be equal to A. So now, this equation will be minus ln of A is equal to time is equal to 0. This is 0. So k1 into 0 is 0. I minus ln of A will be equal to I. We have got the value of I now. Substituting the value of I. Over here, what we get is minus ln of x is equal to k1t minus ln of A. When we bring both the log terms together, we get minus ln of x plus ln of A is equal to k1t. This is negative, therefore we can say ln of A ln of A by ln of x will be k1t, or we can say ln of x by A is equal to minus k1t, or we can write it as x is equal to A minus A e raised to minus K1T. Now, rate of formation of C will be given by C has value Z. Concentration of C is considered to be Z. Therefore, rate of formation of C will be dZ by dt, and here we have K1 and K2 here. So at C, that is dZ by dt, we will have K2 Y, since it is being formed from Y. Now K2 is the rate constant for formation of C from B. Since the rate of formation of B is given by K1x, K1 and the rate of decomposition of B into C is given by K2Y. The rate at which B accumulates. Dy by dt in the system is given by dy by dt is equal to minus dx by dt minus of plus dz by dt, which is nothing but minus dx by dt minus dz by dt. Minus dx by dt is equal to K1x and minus dz by dt is equal to K2y. On substituting the value of x over here, what we get is dy by dt is equal to k1 a e raised to minus k1t minus k2y. Since this equation is first order, differential, since this equation, it is first order differential equation. It can be written as, the solution can be given as y is equal to a e raised to minus k2t into k1 e raised to k2 minus k1 of t divided by k2 minus k1 minus of k1 divided by k2 minus k1. Just put it into the bracket so that there is not much confusion, which is equal to k1a divided by k2 minus k1, which is taken out as common, and e raised to minus kt minus e raised to minus k2t. So k1 and k2. But if we come over here, we see that z is equal to over here, we can see z is equal to a minus x minus y. So let us use this. Z is equal to a minus x minus y. So we are having z is equal to a e raised to k1t minus k1a divided by k2 minus k1 inside the bracket e raised to minus k1t minus e raised to minus k2t. Or you can say z is equal to a divided by K2 minus K1, which is common to K2 minus K1 minus K2 e raised to minus K1t plus K1 e raised to minus K1t minus K1 e raised to minus K1t plus K1 e raised to minus K2t. Just adjusted a little bit so that I can arrange the equation here. We are having K2, K1 e raised to minus K1t. We are having e raised to minus K1t, K2 and K1. So we will bring this in as common, and what we have is another equation, that is z is equal to A divided by K2 minus K1 inside the brackets K2 minus this, and this we will bring together. K2 e raised to minus K1t the remaining is K1 and K1 e raised to minus K2t. The rest others, this is minus, this is plus. I'm sorry. This is minus, this is plus. So this is plus, this is minus. These two will get cancelled out. What we are remained with? K1 and e raised to minus K2t. So we'll bring this in common. So now what we are having is minus K1 minus K1 e raised to minus, since it is a minus symbol here, there is a minus symbol here. So minus into minus will become plus, which is there over here. So this will come in common over here. minus K to T. Now, if we plot a graph of concentration versus time, I'll do it over here. Concentration versus time. Plot between A, B, C of any consecutive reaction in which A is going to B is going to C. The graph will be somewhat like this. A, the initial concentration is 0, and as with the time the concentration will keep on reducing. Now this is A. The plot of A, it is disappearing. Then next, plot of B, concentration of B, because it will form products. It will form, B is a product of A. So the concentration will change, will increase, and then again it will reduce. Initially, B is a product, so the concentration will increase initially and then slowly it will decrease. Let us see C. Concentration of C. C is our final product. So concentration will continuously increase. Initially it was 0. It will slowly increase. That is, we can say if A is equal to 1, then K1 will be equal to 0.01 and K2 will be equal to 0.02. If a graph of X, Y and Z is plotted. Now from this plot, we can conclude that concentration of A falls continuously. Concentration of C rises continuously. Concentration of B rises to maximum and then decreases with time. Therm, 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 aldecom, Position of acetone and hydrolysis of an ester of diabasic acid. We can say example diethyl succinate. All these are ester example. This is an ester example. All these are examples of consecutive successive reactions. So in this topic, I have completed consecutive reactions, chain reactions. A chain reaction, it is one in which products of the reaction, now A is the reactant and this B is the product. So the product of the reaction initiates a long series of self-repeating steps. Now chain reactions may differ. Chain reactions may differ in many respects from homogeneous reactions. So I'll conclude my topic today with this. The next class I'll be taking up general characteristics. I have completed all the three: kinetics of complex reactions, that is opposing reactions, parallel reactions and consecutive reactions. The next video I'll be making on general characteristics of these type of complex reactions. Do watch it. Keep watching. Thank you.